Hi everyone, my name is Richard. I'm a PhD student at the University of Münster in Germany, and today I want to present joint work with my colleague Ari Rasch and my supervisor Sergei Gorlatch titled Code Generation and Optimization for Deep Learning Computations on GPUs via Multidimensional Homomorphisms. In this work, we present our work-in-progress code generation and optimization approach for deep learning computations. It is based on the formalism of multidimensional homomorphisms, or MDH for short. We are able, with our approach, to achieve high performance for popular deep learning computations taken from real-world neural networks by exploiting the already existing MDH GPU code generation and optimization approach. And we show that we are more expressive than state-of-the-art deep learning abstractions as provided by TensorFlow, for example. MDH is capable of expressing not only single deep learning computations like matmul and convolution, but also multiple deep learning computations as a single MDH expression. And this enables MDH optimizations like parallelization and tiling across the computations. Let's start with a high-level overview of the MDH formalism, and I won't dive into too much detail here because of time reasons, but I'm happy to answer questions at the end. So matrix multiplication, or matmul, is conveniently expressed in MDH using exactly three higher-order functions: input view, MDHom, and out view. And just a few more details on those. Input view and out view prepare the input and output data of matmul, meaning they take matrices A, B, and C and specify which elements of them are read and written. MDHom specifies the computation part of matmul, so it specifies that we multiply elements in A and B, concatenate them in the first two dimensions, and sum them in the last dimension. MDH allows us to conveniently express data parallel computations, in particular is used in deep learning, and automatically generate CUDA code for them. These are 5 popular deep learning computations expressed using MDH. For example, we can observe that expressing batched matrix multiplication requires only slightly adapting the matmul expression from the previous slide. And we can also observe that pointwise computations like multiplication and subtraction, or computations that are even more specific to deep learning, like biset gradient, for example, are also conveniently and naturally expressed in MDH. A further interesting observation is that our approach is also able to express multiple deep learning computations as a single MDH expression. This process can be automatized by exploiting MDH's formal properties, and we will demonstrate that in our future work. So here on the left, you can see the TensorFlow implementation of a deep learning subgraph taken from BERT's neural network consisting of multiple deep learning computations. And we are able to express the subgraph as a single MDH expression on the right. And this allows MDH optimizations like parallelization and tiling, for example, to be applied across the deep learning computations instead of optimizing each computation individually, resulting in higher performance. We have evaluated our MDH-generated code on NVIDIA V100 GPU and compared it to well-performing machine-in-hand optimized approaches on real-world data sizes taken from the BERT neural network. For example, on the top left, you can see that we reach a speedup of 2.9 times over Apache's TVM using its recent ENSO optimization engine for biset gradient. And we also reach a notable speedup of 4.9 times over TensorFlow, which is optimized specifically for deep learning workloads for a subgraph of the BERT neural network. So thank you for listening. This is work in progress, so we are grateful for any feedback and questions. So we are happy to get in contact with you. And we also provide an artifact implementation on the bottom left if you are interested in more details or would like to execute the experiments yourself.